And we are all back in another video. We're back in another live stream. Crazy. We're doing like daily live streams now. I don't know how we're doing that, but we're doing it. Maybe because we have a lot of homework. And of course, the number one question you all must have for me is how much did I enjoy my long poop yesterday? Because I believe I did mention that in my last live stream. And I enjoyed it pretty well. Thanks for asking. Anyways, today we are doing a new concept in Calc 2. Yesterday we saw partial fractions, barely finished it. We stayed up like till 12:10 a.m. just doing some coding because we also have other classes, not just this one. And today's video, in fact, let me share my screen. In today's video, we have even more to do. So I shared my screen so I can show y'all what I have left for this module. This is an accelerated course. If in case you guys did not know, it's 6 weeks long and there are 4 modules. So it's a week and a half per module. We did this last Monday. Today's Monday. So we did this a week ago. The substitution rule was done on Tuesday by us. We did this on Wednesday. This took us 3 days and we completed it on Saturday. It was a very tough concept. We did partial fractions yesterday, and today we are doing approximate integrals. Tomorrow, and this is due for Wednesday. Tomorrow we do improper integrals, also due for Wednesday, and our review for test 1, and our test 1 is due on Thursday. Then we begin module 2, which we will see some applications. I'm not sure if it's going to be easier. The applications of derivatives for Calc 1 was much harder than just the derivatives. But again, integrals are much harder than derivatives. Who knows if the applications are going to be easier? Hopefully they are. Hopefully they are. Hopefully. Then we have some series. I heard some of these are tough, like Taylor series or power series, whatever, convergence tests. And then we have parametric and polar curves. Well, hopefully that goes well. 6 weeks. Let's do this. It's nearly an assignment per week. An assignment per day. My bad. So it gets tough like that. And hold on, I don't think I like my camera like that. What if I put it right there? Oh, if I move it there, it looks closer. But if I put it there, it looks farther. You know what? I think that's okay, right? Think y'all can see me clearly? Oh, no. Hold on. Actually, I wanted to test this out. If we put this, there we go. And y'all will see me do work like this. That's how y'all will see me do work. It's actually not bad, is it? I mean, because if I take it off and I put it around there, you see me like that. But here it's totally different. I think it's more Sigma, if you ask me. So that's what we will be doing. You can see my iPad right there. And yeah, will just see me work. Well, since no one is watching, we will begin now. Because there's nothing left to talk about. Since you guys aren't there. So this video luckily was only 16 minutes long. We watched the first 12 and we covered the left, the right, the midpoint, and the trapezoid rule for Riemann integration. It was cool. And by the way, I already saw these first 3, left, right, and midpoint. I just saw the trapezoid, but I mean I think I'm getting it overall. We have one more to see, which looks like he'll cover in the last 4 minutes. Simpson's rule, but I think we need to know the Simpsons rule. So I guess we could watch this quickly. Let's do this. So it's gonna begin also taking notes over here. Simpson's rule. Okay. On each consecutive pair of intervals, the curve y equals f of x is approximated by a parabola. Interesting. on each consecutive pair of intervals. Oh, so that probably explains this diagram right here. I see, okay. So do they use a parabola to estimate an area, or do they estimate the area of a parabola? I'm not sure, but let's see. In fact, I'm just gonna open. Oh wait, already have it right there. Yeah, we saw that. We saw that. Very easy, not bad. Okay, so n must be even. Okay, let y sub I equals f of x sub I. Okay, doesn't look too complicated. The integral using the Simpsons rule equals delta x over 3 times y sub 0 plus 4 times y sub 1 plus 2 times y sub 2 plus 4, 2, k, 4, 2, okay. And with the pattern, 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Okay. By a parabola. Interesting. So, uh, CR, what was it going to write curve? Curve y equals f of x. Approximated approximated by parabola. I spelled out PA. Parabola. Okay. I see. I see y'all. Gotcha. Interesting. So we have x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, x sub 7, x sub 8. So 2, 1, 4. Wasn't that the pattern? All right, well, clearly we go up. Oh, no, no, no. 4, 2, 4, 2, 4, 2, 4, 2, 4. Okay, let's write that formula down. Hopefully we understand where it comes from. Oh, okay. And is 3 just n, or is 3 like always? Hold on, I'm just gonna write from a to b, f of x dx equals. I see, okay. Yeah, here we have the 4 and then the 4. Okay, gotcha. Okay, so first, nothing multiplies, or 1 multiplies f of x sub 0. Then we have 4 times, oops, dude, no, f of x sub 1 plus 2 times f of x sub 2 plus 4 times f of x sub 3, plus, and oh, and f of x sub 4 is the last point, so f of x sub 4, close. Yeah, okay. Mhm, mhm. Oh yeah, look at the trapezoid. Becomes much more accurate. The midpoint also becomes pretty accurate. The right and the left don't really become as accurate, unless I'm reading this wrong. And the Simpson rule is the most accurate. Right, uh-huh. Yeah, uh-huh. Like 10,000. So Simpson is the most accurate far. I think this is important. Yeah, in general, when n multiplied by k, here for left and right, we mul decreases by factor of k. The error for the trapezoid and midpoint rule decreases by factor of k squared. Error. I had a feeling that they're going to ask us this in the homework, so we should just write it down. Awesome. Very cool. Very, very cool. So that is the entire video. So we should have no doubts within the homework. We should have no doubts. We should not even struggle. This does not even seem that bad. I don't see how this can become bad. I don't. But let's do it. Oh, great. We have 21 problems. Oh, wow. That's a lot of problems. Looks like the key for this is to go quick. Here, so I'm going to take a picture. This. The midpoint rule. The trapezoid rule. Very good. And finally, Simpson's rule. All right, we have these pictures. There is absolutely no reason for us to struggle as we have done in the last ones. And let's take a picture of the example, right? Because why not? To go extra safe. Now I am going to split my screen. So what I'm going to do. How do you split the screen? All right, I'm going to go to photos. Oh, I remember that. That was pretty cool. Where do these photos come from, bro? What's this? Bro, like old photos, whatever. So let's split this. Let's put this up here. And let's take good notes. Okay, here we go. It is time to lock in. There is no reason to struggle right here. It is time to lock in. I'm telling you guys. I'm telling you. It is 12:13. Huh. Yeah, I'm also wondering to myself, it's also pretty late. The thing is that since I stayed up till 12:15, what? 12:15 yesterday. I believe I woke up today like at 6:50. Then I fell back to sleep. And then I woke up again at like 8:30. I did my devotional around 8:15. And then I think after that, what did we do? I just hung out with my brother, played with the dog, ate breakfast, and then around 9:45 we begun math, watching lecture. Then, after that, I think I ate breakfast. Then I came back around 11, finished watching the entire lecture. But then we're back. Let's do this. So, question one. Question one. And by the way, first I'm gonna. So they're asked, given the following integral and value of n, approximate the following integral using the method indicated. Round your answer to 6 decimal places. So what we're going to do is open up Desmos. This is going to be extremely vital for our calculations. Let's do this. So oh wait, is there a way I can split the screen? Yes, there we go. Perfect. We're good. So first, trapezoidal rule. Let's open that. Where's the trapezoidal rule? It's right there. So what's smart charging is on. Don't show this again. But cool, I really appreciate it. So let's write down our integral. We have the integral from 0 to 1. Where am I already? Okay, good. 0 to 1 of e to the power of 4x squared tough dx. And we need to evaluate it at n equals 4. So trapezoidal rule. This is going to be approximated to. Oh, first let's calculate delta x. So what is delta x? Delta x is going to be 1 minus 0 over 4, 1/4, or 0.25, depending on how we want to write our answer. So this is approximated to 0.25 over 2 times, well, oh, and first, what is going to be, all right, and we need n equals 4. So x sub 0 will equal, oh wait, but hold on, depends on, no, it actually does not depend on anything. 0. X sub 1 equals 0.25. X sub 2 equals 0.5. X sub 3 equals 0.75. And x sub 4 equals 1. And we need n equals 4. So, yeah, this is probably going to take longer than we think. So this is going to be f of x sub 0. So this is going to be e to the power of 4, e to the power of negative 4 times 0 squared plus e to the power of negative 4 times 0.25 squared plus e to the power of negative 4 times 0.5 squared plus e to the power of negative 4 times 0.75 squared. And actually, I think this is wrong. Do we begin from 1 or 0? No, it's 0. Oh, but you do it for, hold on, bro. So this is going to be, oh, and then do we do, plus e to the power of -4 times 1 squared. So simplifying, okay, in fact, I'm just going to write this in Desmos. 0 squared is 0, -4 times 0, e to the, okay, so e to the power of 0, that's 1, plus e to the power of -4 times 0.25 squared. And in fact, here we're just going to do e. There you go. And here we're just going to do f of 0 plus f of 0.25 plus 5 plus f of 0.75 plus f of 1. That looks correct. I want to see if I got the answer correct. Yeah, that's incorrect. So it looks like we did something wrong. What could we have done wrong? Oh, 6 decimal places. So 1, 2, 3, 4, 5, 6. So how do we round from there? 100. Oh, whoops, we forgot something very important. The 2's. All right. That should be correct. So I'm just going to input the... Okay. All right, we have the right idea. Good, good. Let's oh wait, but we want the... All right. 1, 2, 3, 4, 5, 6. If we do 10, do we still get it correct? Good. All right, midpoint rule. Using the midpoint rule, we get 0.25 times. In fact, this is worth doing in Desmos. It's 0.25. And we're gonna have. All right. So first of all, we're gonna have this 1/2 times 0 plus 0.25. That is going to be the midpoint. F of, oh, no. Is that only the x value? Hold on. Oh, that's right. That's only the x value. So F perfect. Plus F of this. Whoops, what? Why? Oh, right. And that's going to be 0.25 times 0.5 plus F of 0.5 plus 0.75. And this is going to be all the way until n. Oh, wait, no, pause. That's 1, all the way to 2. I think understanding. Okay, hold on. Oh, and then one more. Okay, good. It looks good. Unless I'm missing anything, I think That looks good. That's wrong. And why is that? Mm-hmm. 4. Right, in between each of them. Uh-huh. Wait, what in the world is this plus k? Oh. Mhm. 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 Okay, this is one of those things that we gotta debug now. Hmm. Bro. Hmm. Oh. Oh, that's why. Okay. There we go. Perfect. Now we just need Simpson's rule. In fact, I'm going to put the iPad right here. Since n is even, we can do this. So we're going to get 0.25 over 3 times, okay, so f of x sub 0 Whoops. And what is x of 0? 0. Plus 4 times f of 0.25, I believe, because yeah, x of 1 is 0.25, plus 2 times f of 0.5, plus 4 times f of 0.75. And then plus f of 1. There we go. 1, 2, 3, 4, 5, 6. Very good. That was not complex at all. But I see that this is all about going quickly. It's all about going quickly, everyone. We can do this. Wait, what? Oh, it's that part. All right, let's keep going. A radar gun was used to record the speed of a runner during the first 5 seconds of a race. So T of S. So this is time-based. Oh, I'm sorry. What's T? Distance. Distance-based. Why do they have to use T? Distance-based in seconds. So, what do we have? So T, distance. Wait, a radar gun was used to record the speed of a runner during the first 5 seconds. So in 5 seconds, so this is seconds, right? T of S seconds, I guess. Anyways, use Simpson's rule to estimate the distance the runner covered during those 5 seconds. The distance. So it looks like we're going to have to integrate. Because here we have a speed, that's a velocity, I think. Yeah, v of t. And to get the distance, we're going to have to integrate. Let's do it. Oh, cool. I see. So the way I see this question is, let's see, I'm confused. Why do they use a function to simply measure time? The distance the runner covered during those 5 seconds. Okay. So in 5 seconds, he covered 10.9 feet. So I'm trying to understand this. Yeah. 3 seconds, 3.5 seconds. Oh, I'm sorry. I'm dumb. The bottom row is the velocity, I think. All right, let's just go for it. We won't understand unless we begin. So first, okay. All right, here we go. x sub 0 equals 0. X sub 1, let's say it equals 3.1. X sub 2 equals 3.5. X sub 3 equals 6.95. X sub 4 equals 7.45. X sub 5 equals 8.85. X sub 6 equals 9.75. X sub 7 10.45. X sub 8 equals 10.55. X sub 9 equals 10.9. And finally, x sub 10 equals 10.92. Use Simpson's rule to estimate the distance. Gotcha. So these are our x's. These are our x's. Okay. So what do we see here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Hold on. If I have a partition, 1 partition, 2 partitions, 3 partitions. If I have 4 points, that's 3 partitions. That's not 4, right? We have 3, we have 3 intervals. Here, n equals 10. And delta x equals, well, this is going to be, hold on. So, bro, think. This goes from time 0 all the way to time 5. So I believe this is 5 minus 0 over 10, or 1/2. Because 5 over 10 is 1/2. 1/2. I see. So I think that's all we need. So now what do we do? Use Simpson's rule. And let's go. We have it right here. So delta x over 3. Okay, yeah, I don't think we need to write that. Let's just write it. So we have 1/2 over 3 times f of 0 plus 4 times f of 3.1 plus 2 times f of 3.5 plus 4 times f of 6.95 plus 2 times f of 7.45. Okay, not bad. It doesn't seem bad yet. Plus 4 times f of 8.85 plus 2 times f of 9.75 plus 4 times f of 10.45 plus 2 times f of 10.55 plus 4 times f of 10.9 plus f of 10.9. We did not multiply that last one because you do not multiply. Oh, sorry. No. That does not matter. Anyways, now we just have to let her rip in Desmos. So 1 over 2, all of that over 3. That's the same thing as 1 over 6. So we're going to write that. Algebra proficiency. Proficiency is important. So we're going to take, okay, let's say this is g of x. Fine, let's say that's f of x. Now we have g of x. What does it equal? Oh, Wait, pause, pull the brakes. We don't even have a function. Why did it put it in F? Wait, am I stupid? Okay, hold on, pause. We 106. In fact, I don't know why we wrote all of that. We just wasted a bunch. No. It's fine. We we fulfilled our conceptual understanding, but it was not necessary at all. So 0 plus. Oh no. Here, in fact, I'll just follow it over here. So we have 4. Wait, no. Wait, pause. Oh, okay. Wait, I think I did this wrong. X sub 0 is 0. X sub. Okay, so yeah, I did this all wrong. I understand why I got it wrong, so I'm not going to fix it. But it was wrong. 4 times 3.1. So we get 0 times 0. Yes. Plus. Sorry, we had 1 times 0, I believe. Plus 2 times 3.5. Plus 4 times 6.95. Dude, 6.95. Plus 2 times 7.45. Plus 4 times 8.85. Plus 2 times 9.75. Plus 4 times 10.45. Excuse me, that's rude. Times 2 times 10.55. Plus 4 times 10.9. Plus 10.9. Now that, my friends, is our answer. And that was right on the first try. Let's go. Do y'all see? We are literally cooking in here. Let's go. And we go 40. Oh, what? 47 minutes? How is it even possible? Okay. That's crazy. I remember when I was a kid, and every time I played Brawl Stars, my favorite video game at the time, I always complained. Time passes so fast when I'm playing video games, and time passes so slow when I'm doing homework. That never happens now. I see that when you're in college. In fact, time passes even faster when you're doing homework. When you're coding, bro, that's incredible. We got some physics. Now we can look smart. Let's go. So we only go like 10% of the entire thing. Okay, gotcha. Looks like a very nice day outside, and I'm not gonna lie. Look at those clouds. A very nice day. It's actually quite nice in this room. I'm not gonna lie. Okay. Come on. How long do we go? We go 48 minutes. Cool. All right, let's keep going. Consider the integral approximation t of t sub 20 of the, okay, sorry, I'm just gonna go to the bathroom real quickly, and then we will lock in again. Here we go. So consider the integral approximation t sub 20 of the integral from 0 to 4 of 4e to the power of negative x over 4 dx. Does t sub 20 overestimate or underestimate the exact value? T sub 20? What is t sub 20? Oh, the integral approximation. Why is it called like that? What is t sub 19 or t sub 21? Okay. Find the error bound for t sub 20 without calculating t sub n, using the result that error of t sub n is less or equal than m times b minus a cubed over 12 uppercase n squared, where m is the least upper bound for all absolute values of the second derivative of the function for e to the power of negative x over 4 on the interval, on the closed interval a comma b. Wow, what am I reading? I don't know. Let's get some help to understand. Oh, we're bringing back concavity. Okay, let's do this. So, to decide whether t sub 20 underestimates or overestimates the integral, think about the concavity of f of x. Guess let's put it in Desmos. Gotcha. Yeah, it never goes negative. It's always greater than 0. An upper bound, okay? What is b minus a, though? Or what is a and what is b? Where did we get 0, 7? All right. I might have to skip this problem because I don't exactly understand. No, but I just want to get it over with, so we don't have to come back to it. That's all right. Gotcha. Okay. I see. I see. Okay. So that means, okay. But what is an error bound though? Okay. So think about the concavity. Do we get the same function? Oh, hold on. All right. So I'm just gonna write the function down. Okay. So to decide whether t sub 20 underestimates or overestimates the integral, think about the concavity of the function. Oh, well, that was fake. Don't know why I did that. Okay, so let's think about it. We have e to the power of negative x over 4. So this is 4 over e to the power of x over 4. So e is growing. But it's decreasing actually because it's 1 over. So it makes sense, right? Yeah, so that's the concavity. Infinity all the way to 0. Right, and that's exactly what we see. Infinity all the way to 0. Calculate f prime prime. I don't know, but okay. So first, what is f prime of x? That's going to be 4 times, well, e times, e to the power of negative x over 4 times the derivative of the inner function, negative x over 4. That's going to be times negative 1/4. I believe so. So 4 times negative 1/4, that is simply negative 1. So we're left with negative e to the power of negative x over 4. And then taking the derivative of that, we get negative, well, I'll just open square brackets, e to the power of negative x over 4 times the inner function. It's going to be negative 1/4 once again. So then negative 1 times negative 1/4 is simply 1/4 times e to the power of x over 4. So what you got? That's exactly what I got. And by seeing the function, we know that it's greater than 0 for all x. So t sub 20 overestimates the integral. Good to know. The upper bound, oh wait, but that's what they're asking us. So it's not good to know. It's actually essential to know. Anyways, the upper bound of the integral, on the error. Let's put this over here because it makes us look cool. Actually, no, it doesn't. Kind of nice. So we have the absolute value of t sub n minus the integral from a to b of f of x dx. Oh, so the upper bound on that error, well, I'm just going to make this neater. It's going to be, well, why not, right? K sub 2 times b minus a to the power of 3 over 12n squared, where k squared is an upper bound for the double derivative of f of x on the closed interval ab, and upper bound for the absolute value of the double derivative on 0 to 7, for us is going to be 0 to 4, is 0.25. I'm sorry, what are we doing? Are we replacing? Oh, the upper, so did he replace 0? Negative 0 over 4, that's negative 0, that's 0. E to the power of 0 is 1, 1/4, 0.25. Gotcha. Oh, I see. Well, I believe we also get 0.25. Wait, and 0.25 squared, that's going to be like, I don't know. Wait, didn't do, oh, sorry. Sub 2. So we have 0.25 times 4 cubed over 12. And what's our n? Are you going to tell us the n or not? Well, you got 20. But why 20? Where did the 20? Oh, that's right. We also got 20. Well, let's just type that in, right? Whoops. 0.25 times 4 cubed, or 64. That's 16, right? Times 400, we get this. Is that our answer? And that is our answer. Oh, but we did not answer this. Well, that overestimates. And we're correct because we're so good. Let's go. That's 3 questions out of 21. Oh boy. Let's do this. I mean, these aren't hard questions, actually. I'm not having to use a lot of help. In fact, I don't think I had to use any of help except for the third question that I had no idea what they're talking about. But no, I mean, this is easy. This is actually not very bad. So use 6 rectangles, meaning that n equals 6. Whoops. To find an estimate of each type for the area under the graph of f from 0 to 12. I see. Hmm. Hold on. Use 6 rectangles to find the estimate of each type. What do you mean by each? Okay, it's fine. It's fine. So let's see. So this thing is decreasing. Are they going to tell us? If each type, does that mean like of each rule? No, I don't think so. Hopefully not, because that would be pretty long. All right. Take the sample points from the left endpoints. Left. Okay. So we get there you go. So we get so first, what is delta x? Two. So we have 2 times so what is x sub 0? Oh yeah, left endpoints, right. So yeah, we begin with f of x sub 0. F of x sub 0 looks like it's 0 plus f of x sub 1. So 2 plus 4 plus 6 plus 8 plus 10.
1, 2, 3, 4, 5, 6. That's good. Really easy. 10, 20, 30. 2 times 30 is going to be 60. I think that's correct. Is that how they wanted to do it? Perfect. Okay. We're good. Let's keep going. Is your estimate an underestimate or overestimate of the true area? Well, it depends what the true area is, right? Let's think about it. Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 24. We have 24. We have 36, 35. We have 35.25. 35.25. 46. Oh, wow. Yeah, no, I'm not sure. That's okay. I'm just gonna fight the no. Hold on. So underestimate or overestimate? Well, bro, it depends on. Let's see. I mean, do you want me to find the actual estimate? I think I'll need the actual function for that though. Underestimate or overestimate of the true area. Let's see how they do this. Okay. All right, it's fine. The right endpoints is going to be 2 times 2 plus 4 plus 6 plus 8 plus 10 plus 12. That's going to equal, so 2 plus 12, 14, 28, 28 and 42. 2 times 42, 84. So we get 84. The midpoints, we get 6, 3, plus 10, 5, 7, 18, 9, 10, 10, 25, 50. This is overestimate and overestimate. Oh, this is also 84. So we have 2 times 14 plus 14, that's 28, plus 14, that's 42. 42 times 2, that's 84, isn't it? Looks like that's an underestimate, so I should get. What am I missing here? And the 50 is also incorrect. Let's see. What did we do wrong? Oh, wait. Whoops. And this was plus 1/2, 10 plus 12. So therefore, 22, 11. There you go. So 12 plus 12, 24, plus 12, 36. 36 times 2 is 72. And why? Let's see, bro. What in the world is going on? Let's see. Think. Come on, David, think. Yeah, so delta x is 2. Let's see. What am I missing? So we have yeah, 84. Am I doing something? No, okay. Well, obviously I'm doing something wrong. Oh, wait, what? Uh, wait, oh, great. I mean, these are not x values I'm adding y values. What are the y values here? Oh, to estimate. So we begin here. That is 1, 2, 3, 4, 5, 6. 6 plus. That looks like a 5.5. That looks like a 5. That looks like a 4.25. That looks like a 3.25. And that looks like a 2. So adding this up, $52. And what? Oh, now it's only midpoint. So it looks like we are also going to estimate the midpoints. Yeah, so this is actually wrong. Don't know why we did that. Midpoint. So it's going to be here. It's going to be 6. Okay. 6 plus 5.75. 5.25. 4.75. 3.75. 2.75. 56.5. There we go. Very good. Very good. That's much better. I started streaming 67 minutes ago. Wait, 6-7. Oh, what are the chances? Oh, well, thanks for letting me know. Thank you. Yeah, 6-7 has been haunting me. My iPad yesterday was 67%. My brother's computer was 67% too. What else was 67%? Oh, I think I got a 67 result in my coding project in a program I did. Oh, and also my reading was 67%. I finished it yesterday at 12 a.m., but we got we got an 100, but before that we had a 67%. So incredible, isn't it? 67 is everywhere. I wonder what Bible verses have 67 in it. Crazy, crazy, isn't it? How has 67 or 67 haunted y'all? All right. Well, that's fun. Okay. Okay, well, I believe we should get back at it because even though we're cooking, we aren't close to done. But let's do this. Shouldn't be too hard. Take the sample points from the left endpoint. So we have, oh, and by the way, from 1 to 9. So delta x, okay, hold on, and 4 rectangles. N equals 4. From 9 to 9 minus 1, all of that over 4. 2, right? I'm just going to get rid of these things. There you go. 2. Delta x is 2. We have 4 rectangles. So left endpoints, we're going to get, in fact, maybe it's better. Split the screen. There you go. So we have 2 times. So left endpoint, we begin at, so this is f of 1, and that's 2, plus 2.25, plus 2.75, plus 3.5, plus 4.25. Oh, without 4. There we go. So this is going to be 21. And let's see whether it is an underestimation or overestimation. So 2 times, you get 2.25 plus 2.75 plus 3.5 plus 4.25. This is 25.5. Using the trapezoidal rule, let me see if I remember. So delta x is 2. 2 over 3 times what? Oh boy, what was it? 4242. No, that was the Simpsons rule. This was, oh, okay, I remember. So we begin at 2, I believe, plus 2 times 2.25 plus 2 times 3.5 plus 2 times 4.25. I believe that's correct. Oh, whoops. No, and then there we go. delta x is 2. First of all, is this correct? So it's only the trapezoidal rule that phew, I thought I ended the live stream. So let's remember. Oh, it's over 2. So here we have nothing there. 27.5. So under. Oh, hold on. So the T of 4 was or the T of 20 was a trapezoidal. Oh, I didn't understand that. Oh, and the 27.5 is incorrect. Hold on, so this overestimation then. Okay. Oh, and we begin. Oh, right, dude. There we go. That looks correct. Very good. Very good. We continue. So we have 16 questions left. Okay. I mean, this isn't too bad. But maybe playing a game is not too bad. Because playing a game is kind of fun. Oh, I thought I could kill him. It would have been pretty cool. Oh, a free food for me? Ah, okay. Well, Oxel died. So first place is 25,000. Oh. Oh, dude, look, I'm getting all this food. Dude, I feel so bad for him. No, what? How? That's not fair, bro. That's so not fair. Okay. Oh, that was fun. Bro, what? Oh, yes, a bunch of food. Bro, what? Dude, that's not cool. Let's be pink this time. We're distinct, guys. Oh, let's go. Dude, why do you have to do that? Don't do that. What? Let's go. Uh-oh. Oh, dude. Why did this guy have to be here? Why did he do that? Bro, don't stop. Why am I complaining so much, bro? Let's go. Bro. All right, guess we can play one more game. Let's go. Okay. Ah, great. All right. Well, that was fun, everyone. That was pretty fun. But we are back. We are back to more calculus. Why is bro streaming? Well, because it helps him focus with my homework. 4 likes. Thank you, guys. Twin. All right. Let's go. Let's go. Yes, this is a study stream. This is a study stream. We were taking a break, but now we're back and we're gonna lock in. So here we go. The graph of a function f is given below. Estimate the integral from 0 to 8 of f of x dx using 4 subintervals with right endpoints, left endpoints, and midpoints. Very easy. Okay, so I think we're simply supposed to observe the graph. So delta x is going to be 8 minus 0 over 4, and that's 2. Let's see. So let's estimate this using left endpoints. And let's see, Desmo is right here, this graphing calculator. So since we have 2, so the left endpoints is going to be, first, we're going to have f of 0, which is going to be 2, plus, and then we're going to go down here, that's going to be 1, plus 2, and right here, that's 2, plus, wait, this is left endpoints. Left endpoints, hold on. Right. Plus 2, we're going to go down here, and that's going to be negative 2. And right, it's assigned area, so that's okay. And then 2, we're going to go to 1, plus 1. So I believe this is going to be 8. Using right endpoints, we get 2 plus 1. Oh, wait. 6 right here. 2 plus 1 plus 2 minus 2. Plus 1. We actually begin at this 1 right here. And here we get 4. And the midpoint rule, well, quite easy. Right, and we're evaluating y values, f of x values. 1/2 0. Oh, whoops. 1/2 2 plus 1 plus 1/2 1 plus 2, I believe, plus 1/2. Wait. 1, 2. 2 minus 2 plus 1/2 negative 2 plus 1. And we get 5. That should be correct. And they're all wrong. That's crazy. And how did this happen? Oh, hold on. Wait, so this is right endpoint. So 4, this is 6. Well, that should be correct. These two are correct, but then the midpoints are incorrect. The midpoints, yeah, delta x, 1/2. 1/2, 2 plus 1, plus 1/2, 1 plus 2, plus 1/2, 2 minus 2, plus 1/2, minus 2, and 1. And that's 5. And what could be wrong over here? Midpoint rule. Oh, well, we could also do 2 plus, whoops, actually 3 plus 2 3 plus 2 plus 1, 2, 1, minus 1. And that gives 10. Is that for real? Hold on. So what was wrong with what we did? The midpoint rule. Yeah, we did 2 times 2 plus 1 times 1/2 of that. Interesting. Okay. Well, let's continue. Given the following graph of the function y equals f of x and n equals 6, answer the following questions about the area under the curve from x equals 0 to x equals 6. Okay. So we observe it goes high, then lower, then a little bit higher. Round your answer to within 2 decimal places if necessary, but do not round until your final computation. I see. So use the trapezoidal rule to estimate the area. So we get, so first of all, what is delta x? Delta x is going to be 6 minus 0 over 6, so that's 1. We need 6 rectangles. Gotcha. So the delta x, the width is going to be 1. Beautiful. So then you will do, we will do now, all right, what's next? So what's f of 0? Wait, do we do from f of 0? Oh yeah, all the way to f of n. So what is f of 0? So 2 plus 2 times 3 plus 2 times 4 plus 2 times 3 plus 2 times 2.5. Whoops. Plus 2 times 2 plus 4. I believe that's 35. Hold on. Wait. I might be wrong. So 2 times. So 2 plus 2 times 3. Right there. Am I doing it correctly? I think so. Plus 2 times 4 plus 2 times 3 plus 2 times 2.5 plus 2 times 2 plus 4. Use Simpson's rule. So here we're going to have, oh, hold on. Wait, no. Here we have delta x over 2. So we're going to have 1/2. There we go. So 17.5. Here we're going to have over 3, right? Delta x over 3. So 1/3. Times, so we're going to have 2 plus 4 times 3 plus 2 times 4. 4, 2, 4 plus 4 times 3 plus 2 times 2.5 plus 4 times 2 plus 4. So here we get 17. Oh boy, wow, what happened here? Oh wait. Oh. So we have 1/3. Then we have 2. 4, 2, 4, 2, 4. Why is that wrong? To estimate the area, We have 1/3. 2. Oh, great. And here we had 1/2. Bro, I'm not sure. Oh, round to 2 decimal places. Do not round until your final computation. I don't think I have to round. Yeah, that's exactly what we did. Wait, but why did you get this number? Bro. I don't see why this is wrong. Just like something like that. What? Did we mix them up? So the trapezoid rule. To estimate the area. So we had 1, and then you divided the delta x and f of x sub 0. That's f of 0 or 1. Oh, sorry, or 2. I literally have no idea why this is wrong. Let's see how they did this. Am I not sharing my screen? Oh, I thought I was sharing my screen. I don't know what happened. Oh, I think what happened is I accidentally turned off my computer. My bad. All right, so everything is correct except, so let's see, 1. Sorry, 2. That's 2. 3, 4. 3. That's 2.5. That's 2. But that's 4. Dude, guess I'll have to ask AI or something, but I have no idea why this is wrong. Why in the world are my answers wrong? Verifying that I'm human. Do I look like human, guys? All right, I'll admit, I guess I do act like a robot sometimes. Never goes above 3. Well, it does clearly. Wait, what? Is that 5? Wait. Okay. 3, 5. Then we're back to 3 and 2.5. Oh, so this is 18.5. Round to 2 decimal places and 2.5. I don't know what happened. I was like hallucinating or something, but I swear I saw those at 4. What in the world was that? That's weird. Okay, I gotta go quick because these questions are really easy. I don't know why I'm taking so long. Wait, and how long do we go? We go 2 hours. Okay. So estimate the area under the graph in the figure by using the trapezoidal rule, the midpoint rule, and the Simpson's rule, each with n equals 4. So n equals 4. Gotcha. In fact, let's do it in the iPad. I believe it's better here. So, let's see. So we have n equals 4. Okay, so first, the trapezoidal rule. We have, and delta x equals 4 minus 0 over 4, and that's equal to 1. Delta x equals 1. Oops, and this minus here. Yes. So, wait, and what is next? Oh, yeah, I just went blank. So we have 1/2. In fact, I'll just write this in Desmos. We have 1/2 times, and then we have f of x sub 0. F of x sub 0. 1/2 times f of x sub 0. F of x sub 0 is 0 plus 2 times, oh, and right, 1 plus 2 times, whoops, and this is not 1, don't know why I put that. This is going to be 3 times, sorry, plus 2 times 5 plus 2 times 3 plus 1. 11.5. The midpoint rule. We simply have delta x. Delta x is 1, so we're not going to multiply anything. Okay. So midpoint rule, we have 1/2 times 0 plus 3 plus 1/2 times 3 plus 5 plus 1/2 times 5 plus 3 plus 1/2 times 3 plus 1. 11.5 as well. And then here we have in Simpson's rule, we're going to have 1/3. We're going to have 0 plus 4 times 3 plus 2 times 5 plus 4 times 3 plus 1. All right, this is getting freakishly easy because the last assignments were incredibly difficult, but this is tough. Thank you. Okay. Thanks a lot, whoever you are. Thanks, guys. See, we go 2 hours. The left, right, trapezoidal, and midpoint rule approximations were used to estimate the integral from 0 to 2 of f of x dx, where f is the function, whose graph is shown below. Gotcha. Okay. The estimates were 0.7811, 0.8675, 0.8632, and 0.9540. And the same number of subintervals were used in each case. Same number of subintervals, oh, well, right, yeah. Which rule produced which estimate? I see, okay. Oh, gotcha. Okay, so let's see. So, oh yeah, we had a rule decreased by a factor of k. So the trapezoidal should be the most accurate. Hold on. Let's see. 0 to 2. Okay, so these should be almost the same. So I'll put this and that. All of them are wrong? Yo. Okay, let's see. So if we do left, then if we do right. Oh, so the left hand should be like the greatest and the right hand should be the least, I believe. Midpoint should be somewhere in between. Is this it? All right, so I was right about the greatest and the least. It looks like the trapezoidal rule is going to be the 75. I mean, how was I supposed to know that? Oh, hold on. The trapezoid, okay. Okay. Between which two approximations does the value lie? Well, it must lie between the midpoint and the trapezoidal. There you go. That seems correct. Yeah. Very good. Consider the four functions shown below. On the first two, an approximation for the integral from a to b of f of x dx is shown. For graph number 1, which integration method is shown, this seems like it is left. Let me just make sure. Yeah, it's always hitting the left corners. Is this method an over or underestimate? This is going to be, I believe it's going to be an overestimate. Clearly, since our function is decreasing, or it's decreasingly increasing. Okay, well, it's decreasing its rate of change. So the rectangles are going to be bigger. For graph number 2, it's going to be, this is midpoint. Over or underestimate? Well, this is oh, I see. Looks pretty accurate, actually. Let's see. Here it's missing this part. I believe it's under. On the copy of graph number 3, sketch and estimate. Sketch an estimate with n equals 2 subdivisions using the right rule. So we are going to get a rectangle here, and the corner is going to touch the graph. And then we're going to have another rectangle aligned perfectly where the right corner touches the graph. That's how it's going to be if we were to do that. Is this method? Well, this is going to be Oh, wait, hold on. Wait. Is this under the graph? Oh, well, if that's the case, then we're going to have, it's going to go under here. It's a little hard to tell. Oh, okay. Well, using this same logic over here, yeah, well, that's an overestimate, right? Here, we're going to have, we're also going to have an overestimate. Sketch with n to using the trapezoidal rule. Trapezoidal. Well, I don't think it's going to be any, right? Hold on. In the last problem, trapezoidal was bigger than the midpoint. Maybe it's going to be over. So it's under? Okay. That's under. And under like that. I thought it was going to be over, actually. Oh, okay, hold on. I don't know. And this, using the trapezoidal. I mean, isn't it perfect? Unless I'm missing anything. Oh, well, okay, I see. Well, that looks like it's going to be, okay. I wonder why that's under. It's okay. We got to keep going now. Okay, how many questions do we have left? We have 10, 11. We have 11 questions left. All right, fine. Let's lock in. Estimate the integral from 0 to 1 of cosine x squared dx. Okay. So from 0 to 1 of cosine x squared dx. Using first the trapezoidal and then the midpoint rule. And we're going to have n equals 4. So we have, okay, 3. Perfect. So first, the trapezoidal rule. So delta x, whoops, not dx, delta x, it's going to be 1 minus 0 over 4 equals 1/4. And then, so on. So then we're going to have 1/4 over 2. Wait, 1/4 over 2 or multiply by 1/2? 1/8, times. So this is going to be cosine of 0. Oh, hold on. Trapezoidal rule. So f of x sub 0. So that is cosine of 0 squared plus 2 times cosine of 1. So 1/2 squared okay. So first, x sub 0 is going to be 0. X sub 1 is going to be 0.5. X sub 2 is going to be 1. X sub 3 is going to be 1.5. And x sub 4 is going to be 2. Plus cosine, plus 2 cosine of 1 squared plus 2 cosine of 1.5 squared plus cosine of 2. Putting this in Desmos, let's see what we get. Cosine of 0 plus 2. Okay, will we get that? Yeah, I think that's correct, right? So 5 decimal places. 1, 2, 3, 4, 5. And then we do the midpoint rule. So we're going to have 1, right? Because that's delta x. Oh, wait. In fact, here, I'll just write it down over here. You have 1/2 0 plus 0.5 plus 1/2 0.5 plus 1 plus 1/2 1 plus 1.5 plus 1/2 1.5 plus 2. 4. What in the world? Wait, and this is until 1. Wait, whoops. You think? Okay, I think I did this all wrong. So first, we're going to have 25 here, 0.5 there, 0.75 there, and 1. There we go. Okay, looks better. Then here we're gonna measurement. That's that's not better actually. Well, I'm just gonna copy this. 1, 2, 3, 4, 5. So we do this until 3. And this is correct? Both of them are incorrect. N equals 4. Whoops, I forgot to square this. That's correct. There you go. And why isn't this correct? Because, oh, hold on. Whoops. Cosine of this oh, there you go. Why? Let me see if I did everything correctly. I don't know what's going on. Yeah. Let's see. Oh, what happened here? Oh, 0.25. That is. Oh yeah, you added the x values and then you evaluate. And we have to divide and know. What in the world is going on here? Bro. Let's see. What could be wrong? So this is wrong, right? Yeah. Let's ask why this is wrong. Shouldn't stay here. Wait, whoa. Oh, 1/4. It's 1/4 is not 1. All right, that should be correct. There you go. You forgot. Did you get your x hats for midpoints? Oh, actually, yeah. I think I forgot the delta x. I think I multiplied it by 1 rather than 1/4. Yeah. Like learn. Oh, well, I haven't learned it yet, so that's why I can't use it. I wonder how you'd use it here. Interesting. Hmm. Oh, 7 out of 5 parts have been answered correctly. Zero 4. Oh, so it's greater. So these two? Wait, if I put submit answer. Oh, oh, right. This overestimate, as we just saw. What's this? Oh, wait. No. It's let's see. So since T4's underestimate must be less. Well, there we go. Actually, There you go. Yeah. Well, I'm gonna go to the bathroom, and then we will continue to finish this. Oh. Let's see. Is it possible? So, whoops. Probably. Hold on. Right. Yeah, I guess. So, it is the average. Oh, so it's not possible that they're overestimates? That both of them are overestimates. Oh, let's see. And why is that? I'm not sure. Okay, I guess I'll have to think about that. The absolute value of the error using trapezoidal rule for approximate integral is about twice. So it is true. Trapezoidal rule for approximating a definite integral. Interesting. Okay. And then here, so, okay, it looks like. Consider the approximation for the integral of, the integral from a to b of f of x dx, where f of x is negative, decreasing, and concave up in the interval, in the closed interval a to b. So f of x is negative, okay, decreasing, and concave up. Gotcha, okay. Enter O for each statement if the approximation is an overestimate, and U if it's an underestimate. Write Riemann sum. Right. Well, that's underestimate left is over, trapezoidal over or under? Under, I think. Midpoint Oh, concave up. So it's going to be under then as well. Is a trapezoid a rule wrong? Probably. There we go. That's what I thought. Consider the approximation for the integral from a to b of f of x dx, where f of x is negative. Oh, increasing and concave down. Oh, so it's the left half. It's the left half. And the interval, and the closed interval a to b. Overestimation and u underestimation. So negative, increasing, and concave down. There's that. Midpoint rule. Midpoint rule. Think. It's probably going to be underestimation, right? It's going to be overestimation, left. It's going to be underestimation. Trapezoidal is going to be underestimation. So it's trapezoidal overestimation this time? Gosh. Oh. So it is under. Oh, so is the midpoint rule overestimation? And let's think why that is. It's an overestimation. Okay. I think I can see it. All right, another one of these. So f of x is positive. All right, so now it's above the x-axis. It is increasing and concave up. So the second half, not the first half, but the second half, in the closed interval. All right. Left Riemann sum. That's going to be underestimation. The right is going to be overestimation. The midpoint is going to be overestimation, and the trapezoidal is under this time. All right, so maybe it's over then, right? Oh, so it was under. So is the midpoint under then? Oh, for real? So it's left and right wrong? I mean, it's positive. It's increasing. And concave up, concave up. So increasing. If we have a left Riemann sum, I mean, if we have something like that, we're going to have something like that, something like that. So that's clearly an underestimation. If we have right, that's clearly an overestimation. If we have a midpoint, it's probably going to be an overestimation as well. And trapezoidal, which one? One more. Midpoint gives an underestimation. Oh. So this is under and this is over. I see. Okay. Now decreasing. So if we have a decreasing, so in the first half, if we have this, Left Riemann sum, we're going to have that. Oops. All right, it's fine. Well, that's going to be an overestimation. Well, the right is therefore going to be an underestimation. The midpoint is going to be, which is going to be bigger? I think that's going to be over, and this is under. And there you go. There we go. Now positive and increasing and concave down. So positive increasing left. That's going to be, that is going to be an underestimation. Right is going to be overestimation. The midpoint is going to be, so if we have under and over. So like that. Okay. Positive, decreasing, and concave down. Oh. Okay. So the left is going to be over. Right is going to be under, I think, right? Right. The midpoint rule, under, and so it's going to be over, I believe. Fine, so it's going to be over, and that's going to be under then. There we go. Negative, so now it's under. Increasing and concave up. Okay. So left endpoint, oh wait, negative increasing and concave up. So this is going to be underestimation, overestimate. Oh wait, hold on, wait, pause. But no, actually, no, it's not going to look like that. It's going to look like this. So left. Oops. Like that. So that's going to be an overestimation, actually. That's going to be under. What? It's going to be like that. Yeah, that trapezoid and midpoint, so annoying. Let's see. An underestimation. Oh, right. Because it's in the second half. Okay, no, it makes sense. So this under and trapezoidal, think. I think that's it. All right, fine. So that's also under then. Excuse me, bro. So if we do that, gives an overestimation. Yeah, about the right, that's going to be. Wait, right is over? Why? That's clearly under. I'm confused. Am I imagining it incorrectly? Decreasing, so it's negative, decreasing. Okay. Left, Riemann sum, that's going to be under over trapezoidal, it's going to be over, that's under. Great. Lie above the curve. Overestimation. The midpoint. Under then. Oh, and I forgot. The left and right are opposites. Okay. Biochemical engineers are designing a new athletic shoe. To analyze the impact absorption, they record the vertical ground reaction force, F of T, one. F of T, exerted by a runner's foot on a force plate. The force in newtons is measured every 0.1 seconds. Okay, the data for one full step is recorded below. Okay, so x sub 0 is going to be 0, x sub 1 is going to be 0.1, x sub 2 is going to be 0.2, x sub 3 is going to be 0.3. Okay, and on, right? Use the trapezoidal rule. Okay, so, and this is going to be from 0 all the way to 0.6, right? All right, so n equals 6. So here we're going to have 0. Delta x equals 0.6 minus 0 over 6, and that equals 0.6 over 6, or 0.1. Right. 0.1. So the trapezoidal, we're going to have 0.1 over 2 times. So f of x sub 0, it's going to be 0 plus 2 times 250 plus 2 times 390, all right, and then on, right? 0.1 over 2. 0 plus 2 times 250 plus 2 times 390 plus 2 times 240 plus 2 times 470 plus 2 times 110 plus 0. 146. Impulse, to estimate the total impulse generated during this step. Impulse is defined as the integral of force with respect to time. J equals, all right, well, I think that's it. All right, cool. That actually was much shorter than I thought. All right, awesome. Assignments. And that's actually a very easy one. Okay, cool. So let's go here. Let's refresh. Let's go to grades. Let's collect our award. 26 out of 26. Very good. Very cool. Awesome. Well, that was not bad. Okay, so tomorrow we have improper integrals. And yeah, I think that's it. Let's see, is improper integrals hard? Let's just look at the PDF. Okay, it's just a convergence. Yeah, so I think I'll have to work on This, trigonometric integrals and substitution and partial fractions. These ones I think I already have well. But yeah, in the test this Thursday, we have to practice. Well, everyone, I want to thank you all for watching this video, this live stream with me. It was a lot of fun being with y'all. And I will see you all next time, okay? I'll see you all next time.